Okay, so where we stopped last time was if I've got a single camera, how do I calibrate it? Meaning, how do I estimate its internal parameters like the focal length and the principal point? And we talked about how we do that basically with showing that camera a checkerboard pattern, more or less, that we wave it around, and the positions of those corresponding corners of the checkerboard are what are used to figure out how the camera undertakes the image formation process. We also mentioned this idea of resectioning. Resectioning is basically if I know the real-world 3D positions of points and I know those projections of points on the 2D image plane, I can also use that to form up camera matrices. And so the first thing I want to talk about today is what I would call stereo rig calibration. And so the setup there is that basically I have a rigid bar or a rigid housing that contains a pair of cameras, and these cameras are kind of stuck to this bar so they can never change their relative rotation and translation. Okay? And so now what I want to do is I want to figure out how to simultaneously calibrate these cameras, meaning how can I simultaneously estimate the camera matrices for both cameras. So we already know that since these cameras are separated by a physical length, that these cameras are related together by a fundamental matrix, right? And so the intuition is that we should be able to get at the camera matrices for the two cameras via the fundamental matrix, which we can estimate using some of the techniques we talked about in the last chapter, right? So we know how to find feature points, use the feature points to estimate the fundamental matrix. So now I've got the fundamental matrix. How could I use that to estimate the cameras? Well, there's good news and there's bad news. The good news is that yes, you can do this, but the bad news is that you have some extra degrees of freedom that mean that there is no unique pair of camera matrices that corresponds to a given fundamental matrix, right? And one way to think about this is that, the camera matrices, so if I call this, let's make sure I use the right notation from the book. I assume if I call this P and I call this P prime, right? This is 3 by 4. This is 3 by 4. We know that actually there's 1 degree of freedom in these already, so really there are only 11 parameters to estimate in P because it's unique up to scale. But this F only has 3 by 3, 9 entries, and we know that actually there are only 7 unique degrees of freedom. So basically we've got our, at least, say 20 degrees of freedom for the P's, even if we make the assumption the pixels are square and they don't skew or anything like that. But I've only got 7 degrees of freedom in F. So basically you can see that I've got like way too much stuff to estimate in P and P prime that I could estimate just from knowing F, right? So that leads to ambiguities. What I mean by that is the same F can lead to many different combinations of P and P prime. Okay, so that's the bad news. Now, you could say, okay, well, some of those ambiguities are relatively benign, right? So, for example, let's suppose that, well, it's kind of hard to do with this overhead, but, so one thing I could do is I could say, okay, well, here's my stereo rig. I could rotate it and translate it to here, or rotate it and translate it to here. Clearly, I'm always going to get the same fundamental matrix between the two image planes, but all those are going to have different P comma P prime, and those differences are all attributable to an underlying rigid motion. So you could say, well, okay, 6 of those parameters, 6 of those degrees of freedom of ambiguity are taken into account by this unknown rotation and translation. So what I could do is I could say, okay, I'm going to fix the camera center of the first camera at 0, 0, 0, and I'm going to say, okay, I'm going to assume that I know that the world coordinate frame is kind of aligned up with this camera, right? I guess more accurately it would be like this, where I say, okay, here is the X, Z, and Y is pointing up out of the paper. So I can fix the frame of the first camera. That removes some degrees of freedom, but it still turns out that there are some left, okay? And so we're going to talk about this ambiguity a little bit more in the context of today, okay? So first of all, let's talk about how these fundamental and camera matrices are generally related, okay? So to mathematically formulate what I just said, what I would say is, let's assume that the first camera matrix looks like this. Right? This is like saying this is a 3 by 3 identity matrix, and this is a 3 by 1 matrix of zeros. And this is my camera calibration matrix from before that contains the, focal lengths and the principal points and so on. Okay. So really now there are only 4 things to estimate for this P. And now the P prime, the other camera, may have a different camera calibration matrix, and it's located, at some different place. So it has kind of a generic, R and T that specify where is that camera in the coordinate system of the first camera. Okay. So if I were to think about, what that means, that's like saying that, again, here's my rigid bar that fixes the 2 cameras together. That's like saying that in world coordinates, the center of this camera is 0, 0, 0, and the center of this camera turns out to be minus R transpose T. You can prove that that's true. And so how do I figure out, well, let's think about, first of all, what would be the epipoles of the, stereo rig. What are the epipoles? The epipoles are basically saying if I were to project the camera center from one image onto the other image plane, what would be the point that I would get? And so the epipoles, well, actually these are not too hard to compute. This would be like saying, okay, well, what is the projection of this point onto image 1? I would do it with the camera matrix. I would say that I take P times negative R transpose T. And again, this is up to scale. So what I would get is something like K times I 0 times negative R transpose T 1. And I would get K R transpose T. Really, it would be like, so there's a negative here, but I can kind of get rid of the negative with this tilde that says equal up to scale. And kind of going the other way around, well, I guess technically this is E. This is the epipole. It's like saying, where do I see this point over in this image plane? The other epipole is basically saying, okay, I take the other camera matrix, and I project onto that, 0, 0, 0, and so what I get is K prime T. Okay. So I can figure out where the 2 epipoles are.
And the second epipole is where you would see 0, 0, 0 on
right. Right. So if I project this way, it would say, where do I see that point on this image plane? Okay. So this is just a little bit of homework to figure out where the epipoles are in the images. And if I put all this stuff together, I can figure out, and this is a homework problem that I don't think I assigned because it's a little bit messy, but it leads you through it. So the fundamental matrix in terms of all these camera calibration matrices turns out to be the following. And I'm just going to write this out for posterity. You guys aren't going to need to know it or use it for the moment. So what does this notation mean? If I have some vector with a little x underneath it, my notation is that that turns out to be a matrix that is defined as follows. Let me just write that here. So it has zeros down here, and it has negative C, positive B, that has negative B, positive A, positive A. Oops. This is not what I wanted. Say this again. 0, 0, 0, negative C, positive B, negative B. Should be symmetric across this way. So this is basically saying I have a 3 by 1 vector, and I turn it into a 3 by 3 matrix. Anyway, so this is just a special matrix that plays a role in this equation. And so this basically tells us, okay, if I knew the two camera matrices, how would I produce the corresponding fundamental matrix, right? So this is a useful formula to know because it tells me if I knew what the cameras were, what is the corresponding F, right? What I really want to do in this problem is I tell you the F, how can I unwrap it back to the corresponding parameters, K, K prime, R, and T, right? So that's where we run into this ambiguity problem, right? Because it's easy to take the camera matrices and figure out what the corresponding F is, but it's hard to go the other way around, okay? And part of the reason for that is the following, okay? So the key idea behind the camera matrix is that I form my little image point in homogeneous coordinates as the camera matrix times some point in space, right? So this is the camera matrix. This is a 3 by 4 matrix. This is the scene point in the homogeneous coordinates, which is 4 by 1. I multiply these two things together, and I get some 3 by 1 vector, okay? So this is the way that image projections are formed, but suppose I gave you a P and an X, okay? So I tell you, okay, here is your camera matrix, and here is the point in 3D space. The bad news is that what I could do is I could put in the middle a new matrix H, right, where this matrix is 4 by 4, right? And so as long as I choose any non-singular matrix H, I can achieve for you exactly the same image projection that I would have seen, right? So basically, this says that even if I were to estimate a P and an X that perfectly gave me all the image projections, there would still be this possibility of interposing this other weird matrix in the middle such that I would never know what was the truth, right? I mean, this could be the identity matrix, in which case I would get the original P and X. It could be some rigid motion, in which case it would be like, translating and rotating the stereo rig. Or it could be some sort of weird projective change, which would totally whack my images and points out. So let me just kind of give you a sense of that. So here's a picture that kind of shows, the differences in the 3D points that could occur by applying these, some H in the middle, right? So say the truth is A, right? So if I applied an H in the middle that corresponded to a rigid motion and maybe also a scale change, then the 3D points would look pretty much like the 3D points that I had originally, just looked at differently and maybe bigger or smaller, right? So this wouldn't be so bad. But the problem is that the effects of this H matrix on the 3D world could be even worse than that, right? So there are things that are kind of equivalent to, remember we talked about shear transformations, where basically it's like saying, okay, I push everything along one of the X, Y, Z axes. So that's kind of like what I would get if I pushed this house around along the 3D axes. That would look pretty strange. And unfortunately, you can make even bizarrer things that come from these projective ambiguities, where now, straight lines that I hope were going to be straight and perpendicular are no longer straight and perpendicular. So you can get very weird-looking deformations of the 3D scene. And so the problem is that you can't really tell unless you apply some more information. Like, for example, we'll talk about this more next time, but we'll talk about how you can go from something like this back to something like this with an assumption about the fact that the cameras are not allowed to be too weird, right? So one way of thinking about this is that some of these weird combinations of P and X correspond to camera matrices that we know we would not physically tolerate. For example, they may have pixels that are not square, or they may have aspect ratios between pixels that are not 1-to-1, stuff like that. So we can use some of those real-world constraints to bring our life back to the good position, okay? But for the moment, all I need you to understand is that there is this kind of ambiguity that we have to deal with, okay? And that ambiguity, for the moment, we can't really do anything about. So let me just give you a formula that tells you kind of like what's the best that you can do. If I gave you the fundamental matrix, what would be like one pair of camera matrices that would work, okay? So one possibility for getting, the two camera matrices back from P, or back from F, I'm sorry, is the following. So I can have the freedom to fix my one camera matrix at basically the simplest camera matrix that I could have, right? It sits at 0, 0, 0, and it looks straight ahead, and it has no, it has the identity matrix as its calibration matrix. The other one looks like this. So here again, I'm using this little cross notation that I talked about before. So what does this stuff mean? So here, this is any 3x1 vector, and this is any non-zero scalar. So if I think about this, all the stuff in this equation I can get from the fundamental matrix, right? I know F, presumably I estimate it from looking at point correspondences. I can estimate the epipoles in both images from the fundamental matrix. Those are basically just like the eigenvectors that correspond to the zero eigenvalue. And then I have basically 4 degrees of freedom where I can plug in some other stuff. If I wanted to, I could just say, okay, I'm going to use v equals 0, 0, 0 and lambda equals 1. That would give me a pair of camera matrices that would produce the same fundamental matrix, right? And here I can see that I still have these 4 degrees of projective ambiguity that I don't know how to resolve, okay? So, like I said, there's not much you can do. If you wanted to, you could try to choose this vector here to make the right hand or the left hand 3x3 block of this matrix look as close as possible to a rotation matrix. There's some details about how to do that in the book. But really, unless you have more information, this is about as well as you can do without knowing anything else, okay? So in real life, we often do know a little bit more than this, right? So one thing that we usually know is we can calibrate the internal parameters, the K matrices of these cameras, using this checkerboard algorithm that I talked about last time, right? So life becomes a lot easier if we know K and K prime already, right? Then the only thing we have to estimate is what is the rotation and translation offset of camera 1 to camera 2. So we can, if we know K and K prime already, and like I said, we may be able to get this from plane-based calibration. Then our life becomes a little bit easier. So what I can do is I can basically transform the image coordinates by kind of undoing the camera matrices. Right, this is like saying, okay, undo the effects of the camera matrices, then the two camera matrices are in this particularly nice form where the two camera calibration matrices become the identity matrix, right? So then all I have to do is estimate R and T, okay? And it turns out that, again, I apply this kind of, normalization to the image coordinates, and now I estimate the fundamental matrix again between this new image pair, right? So if I estimate the fundamental matrix using these so-called normalized coordinates, right? So I can still get this matrix F, and in these particular circumstances, when I know the camera calibration matrices, this F has a special name which is called the essential matrix. I mean, it's still a fundamental matrix, but I call it the essential matrix when I happen to know the K and K prime. Okay. And it turns out in this case, I can really nail down what is the rotation and translation. If I estimate this, then what I can do is I can take the singular value decomposition of F, and then there are basically 4 options that I can get. So if I have this singular value decomposition of F, then, for example, my P prime is one of these 4 options. So one of them basically looks like, let me just write this down first and then I'll explain what it means. This W is basically a special matrix made up of zeros and ones. And let's see, U3 is the last column of U. So the idea is that all the stuff I can get from the fundamental matrix, right? I take F, I decompose it into this singular value decomposition, and I obtain basically camera matrices that have to do with the SVD of F, this weird matrix W, and the last column of U, right? All that stuff I can estimate from the fundamental matrix alone, right? And so this tells me that I've gone from a family of 4 degrees of freedom down to one of these 4 options, right? So not 4 degrees of freedom, but literally I only have 4 possibilities. And furthermore, I can tell, I can resolve which of the 4 it is by what I would call triangulation. So what I mean by that is that, kind of these correspond to camera matrices that kind of may have fundamentally the same locations or offsets, but they may be flipped in a different direction. So kind of one way to think about this is that, I have basically 4 options. Either, basically I have these possible pairs of image planes, and there's only one pair of image planes such that if I were to project through the image planes and figure out where the points intersect, they would be in front of both of the cameras, right? So, excuse me. So basically, I can know I've chosen wrong by saying, okay, well, suppose that I had like this candidate, and I looked at where these points intersected. Well, I'd say, hey, this would be behind this camera, and so I know that that can't be the right choice, right? So fundamentally, all you have to do is shoot some rays through the image correspondences that you've got and make sure that they're all in front of both cameras. That will resolve for you which of these possibilities it is. So in practice, it's not really that hard to calibrate a stereo rig because we already kind of knew how to calibrate for the internal parameters of the camera with this plane-based calibration, right? So kind of the overall pipeline would be, you mount your 2 cameras together rigidly, you screw them down so they never move, then you show both cameras the checkerboard, you can probably do the same checkerboard, if the cameras are not too far apart, you can get away with showing it the same images. You use the methods we talked about last time to estimate the K and the K prime. Then you estimate the fundamental matrix between them with a set of feature correspondences, which again shouldn't be too hard to obtain. You could have gotten them actually from the correspondences on the checkerboard that you showed it the first time for the calibration. And then you kind of looked at the SVD of that fundamental matrix and you applied this thing to get RNT, right? So really, the whole thing is not that hard if you've got your nice calibration test pattern, right? So that's not so bad. In theory, you could do the same thing without a checkerboard by basically you've got your cameras mounted on the rig, and you can kind of move this camera rig around the world and look at the pictures that it takes. And if you look at the feature tracks, you kind of use those as surrogates for the checkerboard corners, and you can kind of estimate all the stuff at once if you wanted to. But I mean, in practice, it's not hard at all to just show it some sort of a test pattern that you have in your bag. That's probably easier and faster than trying to get it from natural features. Okay, so that's the quick overview of stereo calibration. Again, if you buy a stereo camera, you generally shouldn't have to do this yourself because, like for example, I bought a. Let me just see here if I have a picture of it. So I have this point-and-grade camera called the Bumblebee. Right, so here's an example of a stereo camera where this thing is already inside of a rigid housing. And you shouldn't ever have to recalibrate this camera because there's no way these cameras are physically going to move, right? They're really bolted together. I mean, if you were doing it yourself, like if you had a kind of DIY, camera rig that you had built especially for some sort of a production, and then maybe you put it in storage and it wiggles around and so on, maybe then you might have to do occasional recalibration. But in this case, I think that you could probably be pretty happy with the calibration. In fact, I also have a, let's see here. Actually, the one I have is got 3 cameras on it, right? It's this guy. Oh, where's my... I saw a picture of it before, but then when I clicked on it, I went back. Anyway, hopefully you could see here that there's this guy, the XB3, right? So I've got this guy actually. So actually it's got, you could think of it as 3 potential pairs of stereo cameras all in one thing, right? So if I wanted to, I could use the shorter baseline, or I could use the larger baseline, or I could use all 3 cameras at once, right? Okay. So any questions about stereo rigs? Kind of like we talked about last time, the way that a stereo camera works or looks in Hollywood is much more bulky than this. And let's just see if there's a... I haven't prepared this, so let's see what it looks like. Right, so here's a good example, I think, where you can see that the 2 cameras are actually mounted off, they're kind of mounted at right angles, and then there's this kind of half-silvered mirror that is passing the images through, and you can still calibrate this camera in exactly the same way because the effective position of the cameras is the same as if they were on a narrow baseline together like this. But the physical configuration of them may be quite different, right? And so...
I think they use this at MPAC.
Yeah, I was going to say, I was just going to say that Eric Amers over at MPAC has done some stuff with stereo filming, and I know that he's made his own kind of do-it-yourself stereo camera, and I'm pretty sure that he did it like this, right? Obviously you can imagine this is not the kind of thing that you could just kind of knock together at home without having a few specialized parts, right? Especially like the half-silvered mirror is something that, you can't just like buy a couple $100 worth of parts and get it to work, but, MPAC can afford to do that, right? Okay. So the thing that I really wanted to, so the main thing that we want to talk about in this chapter is I don't really care about just like a pair of cameras, right? Typically I care about the path of a camera as it moves around an environment, right? So I maybe have a shot that contains 100 frames, right? And now I want to know where was the camera at every point of those 100 frames, right? So really, instead of having like P and P prime, I have P sub K, where K is the kth position of the camera, right? So kind of what we're getting into next is what I would call image sequence calibration. And so, like I talked about in the very beginning, the heart of this problem is this computer vision problem called structure for motion. So you know, I guess you could argue about, like, there may be some fine semantic differences between structure for motion and match moving and camera tracking. In my mind, they're all fundamentally the same problem, so I'm a little bit hand-wavy about it. And so generally, the way it works is the following. So big picture is that, let me just first say the steps, and then I will talk about what they mean. So projective reconstruction is basically the first step. What that means is that, you know, I have a bunch of observations of the ith point in the jth camera, right? And I know that they are related together by the ith camera matrix and the 3D positions at the jth point, right? And what I'm going to do is I'm going to try and estimate these p's and x's to make the difference between this observed projection and this combination of things on the right-hand side as similar as possible, okay? But the problem is that, again, I can insert this, you know, weird matrix in the middle of this and still get very good imagery projections, right? So projective reconstruction kind of gets me there numerically, but doesn't get me there practically, right? I mean, I need to know more to be able to solve the problem I need to solve in visual effects. So the next step is what's called Euclidean or metric reconstruction. And kind of crudely what I would say here is this is basically using facts about form of the camera matrices, right? So this is where I would say, okay, you know, I know the camera matrix can't be this wild matrix. It has to have a nice K, it has to have a nice rotation matrix, and so we'll talk about that part more in the next lecture. And then the third one is what I would call bundle adjustment. And kind of the way I think about this is I parameterize P and X, and then I do some numerical optimization. So kind of one way I think about this is that these two phases, I think, are kind of like initialization of an optimization problem, right? So the optimization problem I want to solve is really called bundle adjustment. And so let me be a little bit more precise about what I mean by the optimization problem. So the key optimization problem aka bundle adjustment, is, well, I know that I have my model that I have these cameras and I have these points, and so here I may have, you know, M cameras and I may have N 3D points, and I also may have like a little indicator variable that is, you know, 1 if point J is seen by camera I, and 0 otherwise. Right? So it's possible that not all the 3D points are seen by all the cameras, right? And so certainly one instance of that is when, you know, if I'm moving a camera around a scene, you know, some of the points are going to fall off one side of the camera and new points are going to be generated on the other edge of the camera. And so naturally, not all the points are seen by all the cameras at once. Question?
It's just assuming that the scene is mostly static.
Yes, it's assuming that the scene is mostly static, right? So you have to make sure that you choose your 3D points on objects that are not moving, right? So you never would want to do bundle adjustment on, like if you're doing a street scene, you don't want your points to be on the pedestrians and the cars, you want them to be on the buildings and the streets, right? So yes, that's a good point. Assuming a static scene. And so what I want to solve is basically I want to minimize, in some sense, the sum over all the cameras and the sum over all the points of the distance between the ijth point and the point that I would get if I had this hypothesis for camera I and this hypothesis for point J. I only need to minimize that distance over places where I actually saw that point in that camera, and my minimization is taken over all the points and all the cameras at once. Right, and as you can imagine, this is some really big minimization problem, right? I've got maybe hundreds of cameras and maybe thousands of points, right? So there's lots and lots of variables in this problem, and that's why initialization of the problem is so important. So if you've ever done any sort of MATLAB numerical optimization, you know, MATLAB will provide you tools like gradient descent and so on for minimizing a cost function, right? But the problem with those tools is they only can find local minima, which means that you want to start your optimization problem close to the truth before you get started. Otherwise, the thing that the numerical optimization may come up with may be locally good, but may be far from the global best thing, right? And so initialization is really important. That's really what we're going to start talking about today. So this thing here, I basically call the reprojection error. Right? This says I want the distance, and so this D here kind of lives in the image planes of the cameras, right? It says in image coordinates, how far away is the observed point little x ij from the projected point that I would have gotten if camera I was here and point J was out there, right? I want to make those as similar as possible. And so one reason, you know, that may not be clear why this is called bundle adjustment is the following. So this may make it a little bit clearer. So what I have are correspondences, right? I know that the black dot matches itself in these three images, and the same with the gray dot and the light gray dot, right? And so I don't know are the white dots, which are the camera locations and orientations, and I don't know these big dots out here, which are the actual 3D positions of the points. And so what I'm trying to do is I'm trying to move these white dots, these big dots around, so that when I look at the set of rays that connect the white dots to all the big dots in the scene, they coincide as well as possible with where they should be on the image plane, right? So you can kind of think about this process as adjusting these bundles of rays, right? So the idea is that this set of rays emanating from this camera center is a bundle, right? And I'm kind of moving this bundle around to make it match up with the image projections that I saw as well as possible, right? So it's kind of a weird name, but this is the idea. These are the bundles in bundle adjustment, right? So that's the main kind of concept here. Okay, so questions about what we're trying to do? Yeah? You still look a little skeptical. No? Oh, hey, wake up. All right. Okay, so let's talk about the first step of this process. I can't get through the whole process today, but I want to get through the first step, which is called projective factorization. Okay? And so let's start with an assumption. So initial assumption. Let's suppose that all 3D points are seen by all cameras. Now that's certainly not a realistic assumption, but one thing that I could do, for example, is I could keep on throwing away points and throwing away cameras until I get a small set of points that is seen by a small set of cameras. So maybe I don't have all the points in all the cameras. So maybe kind of the way I think about this is it's like saying, okay, you know, suppose these are my camera positions, and then these are my 3D points out here. So maybe, you know, since this point is not seen by this camera and this point is not seen by this camera, maybe the first thing that I would do is I say, okay, I'm going to choose some subset of the cameras and some subset of the points such that all the cameras see all these points initially, right? So this is just kind of to seed the problem, right? We'll talk about how we can fill in these cameras and other points later in just a second, okay? So what that means is if I go back to my previous slide, what that means is that basically this indicator variable is 1 for all the points and all the cameras, because I see everything. Okay, it's too late, I've seen everything. So now what I want to do is I say, okay, I've got this system of this, right? I know that every point is seen by every camera. Another way to think about this is that I can replace this tilde with an equals sign by saying there is some scale factor lambda, which I also don't know, that makes this an equality, right? That's like saying that if I knew the kind of scaling between what's on the right-hand side and what's on the left-hand side, that would be represented by this lambda. And so this lambda is what's called the projective depth of a point. So now what I can do is I can form up everything that I know about these x's into a big matrix, right? So that's like saying, okay, well, actually, maybe for my own ease, I'm going to move this lambda ij over here. It doesn't really matter where I put the scaling factor. So I can rewrite this as a big matrix here. So this is going to be like lambda 1, 1, x 1, 1, lambda 1, n, x 1, n, lambda m1, x m1, lambda m n, x m n. So it basically collects all the stuff that I have, right? So this is going to be some massive matrix. It's going to be, well, each of these guys is going to be a 3 by 1 vector, and I have m of them, so it's going to be 3m by, and then I have n points, so it's going to be a 3m by n matrix. We call this the measurement matrix. And then the nice thing about this measurement matrix is that even though it's really big, it is produced by knowing each of the cameras and knowing each of the points, right? So I can write it like this, where I can say, if I were to take the camera matrices and the points, that what's on the left-hand side should exactly match up with what's on the right-hand side. So here, this is a 3m by 4 matrix of cameras, and this is a 4 by n matrix of point locations, right? And I can see that when I multiply these two things together, I get this 3m by n big measurement matrix, okay? And so this is like a key observation, right? This is like saying that even though I have all this data, right, if I were to form this matrix, you know, so again, this kind of comes back to the some linear algebra. So there's something called the rank of a matrix, right? The rank of a matrix basically says how many linearly independent rows or columns can I have in the matrix, right? So in this case, the rank, if I didn't know any better, could be very large, right? Because m is probably big and n is probably pretty big. But when I write it in this way, I can see that the rank of this matrix can be no bigger than 4, right? Because it's made up of something by 4 times 4 by n, right? So, you know, so ideally, rank is at most 4, right? And that observation is what leads us to do this projective factorization idea. So what I can do is I can say, okay, let me call this measurement matrix M, okay? Well, maybe M is not a great word. Actually, now I noticed in my book that I probably shouldn't call it M. Let's call it W, okay? So, again, this is another singular value decomposition thing. So I can take the SVD of W, right? This is 3m by n. This is n by n. This is n by 4, right? That's how the whole thing gets put back together. Oh, let me see. Nope, crap, wrong. This is 3m by n. This is n by n. This is also n by n. My mistake. But this D is supposed to be diagonal, right? And if I look at the entries here of D, what I should get is some stuff here in the first 4 diagonal entries, and then I should get, you know, some very small numbers, right? Because ideally, this measurement matrix is formed up by something that there's only this 4 degrees of freedom. So here, what I should get are 4, you know, non-zero values, and then I should get basically n minus 4 almost 0 values. And so what I can do is I can make a new matrix, let's call it D4, which is just equal to the 4 non-zero values and then 0 everywhere else. Okay, so this basically is saying, okay, I know this should be, it should almost look like this. I'm going to force it to look like that, right? And now I can make a initial guess of this matrix of p's as UD4, right? This is going to be, again, 3m by n. Actually, maybe we better say that D4 is like this, right? D4 is going to be just this n by 4 matrix. And this is n by 4. This is going to be 3m by 4. And then my x, collection of all the x's, is going to be basically the first 4 rows of V transpose. So this is going to be, that's going to be 4 by n. Right? And in this way, I can basically form up candidates for, you know, initial set of p's and initial set of x's, right? So this is a way to say, okay, again, kind of one way I think about this is what would be a set of p's and a set of x's that are consistent with the measurement matrix, right? Now again, due to, you know, noise in the measurements, you know, incorrect correspondences, you know, these numbers here may not be exactly equal to 0, but you can set them equal to 0 and say this is the best that we can do, okay? And again, just in the same way as we talked about before, you know, there are some little things, you know, nitpicky things. You should kind of normalize the points, the 2D, you know, correspondences first. Kind of similar to how we talked about this when we were estimating things like projective transformations. You kind of want to center them to be at 0, 0. You want to normalize them so they have distances square root 2 to the origin, stuff like that. The other thing that I didn't kind of mention is that, you know, in practice, I kind of assumed that I knew these lambdas, right? So if I look back at this thing here, I can't even talk about doing the SVD of this matrix until I know what these lambdas are, right? And so what I could do is I could initialize with all the lambdas equal to 1, and then I can do, you know, solve for, you know, the PIs and the XJs. Then I can compute the new lambdas, because now I have this and I have this and I have the observed little x's, so I can figure out what would be the closest lambdas that would make those two things match up, and then I can iterate until things stop changing. And so there are some, you know, details about how this whole process might work, but, you know, it's not too hard to code up. And so this is called the Sturm-Triggs algorithm. And so the overall algorithm is given in the book. There are a couple little extra steps of normalization errors and stuff like that. So another way I think about this is that, you know, I'm kind of bootstrapping my way up, or I'm kind of iterating until everything stops changing, right? Another way I could think about it as an alternate approach, you know, I could seesaw back and forth. I could estimate the PIs from the XIJs and estimates of this, and then I could go from, you know, the X's So the idea is that if I know two of the things, the third one is easy to estimate, right? And so maybe a better illustration is like this, right? So here, this is kind of like saying, okay, so let's suppose that I knew, maybe this is not the best picture, but let's go back to this. So if I knew the cameras and the corresponding image points, then I could figure out what would be the corresponding x's out in space by triangulating, right? I can kind of push all those rays out into 3D space and find out where the rays corresponding to each point intersect, right? That would be kind of like this picture, right? So if I knew the camera and I knew the point, I can find the 3D position, right? Kind of conversely, if I knew all the 3D point locations and I knew the 2D point locations, then I could figure out where the camera matrices were. That's just this resectioning problem from last lecture, right? So kind of what you're doing is you're alternating resectioning and triangulation, both of which are relatively easy things to do. Okay, so questions about the big picture. So again, at the end of this process, I still have this ambiguity. I can still get very weird P's and X's, right? And so normally what you get out of the end of this process is visually useless, okay? In the sense that if you were to observe where these X's were in space, you would get some sort of a bizarro set of points like figure D here, right? And so you need to do more to make your camera matrices and points match up with what you have, right? But this is the first step. All the information that you really need is inherent in the P and the X that come out of this step, right? The next thing is to say, okay, now I'm going to try and find the best, tweak to these matrices with this kind of H that I put in the middle to bring the camera matrices and points into something that I believe is true. Okay. So one more thing I want to mention, and again, there's a lot of work to really do this robustly and to do it well, right? So for example, like I said, these structure for motion packages that you guys are going to be playing with and that the visual effects people use every day are, based on years and years of research about how to do this problem the right way. And so there's lots of nitpicky stuff that would be difficult to build your own match mover that would do as well as Buju or Synthesize or PF Track or Voodoo or any of those things, right? But one thing I do want to say is that so far everything that I've said doesn't really take into account the fact that these cameras are coming from a continuous motion of a camera, right? So right now, these P matrices, as far as this algorithm is concerned, could have come from anywhere, right? There's no sort of continuity between the cameras, and so we can exploit that. This algorithm I just talked about is good for the problem when, for example, I take a bunch of tourist pictures of the Statue of Liberty and I want to know where were the cameras. In that case, there's no sort of temporal relationship between the pictures that were taken, right? I have no expectation that the cameras could follow some sort of a nice, smooth path. But in real life, our camera is moving along some trajectory in 3D space, and I'm getting like nice little samples of the camera, right? And so I should exploit that fact, right? And so that's talked about in the section called sequential or hierarchical updating. Again, this is really where the secret sauce is, but I would call this kind of like generally some sort of chaining approaches, right? So what I might do is I might say, okay, suppose that I'm going to, so here's a crude idea, right? So what I could do is I could say, okay, I'm going to start with these two cameras, right? I'm going to estimate the fundamental matrix between those cameras, and I'm going to use that to get a pair of camera matrices, right? P and P prime, or P1 and P2, right? And now I say, okay, well, now I saw a bunch of points in 3D space, and I know this P2, and I know where those points were in image 2, so I can basically, build rays out this way. This camera that I haven't looked at yet says, okay, well, now I see some of those same points over here, so I can project those guys back down, and I can estimate P3, right? And then I kind of bootstrap my way along. I can kind of keep on resectioning and triangulating cameras to kind of sequentially estimate these cameras as I move along, right? And the idea is that if the cameras are not moving very much, that estimating the correspondences and then doing the pushing forward and pulling back process shouldn't really be that hard to do. And so kind of what you're doing is, if these are the corresponding images that you get, what you're doing is you're saying, okay, I'm going to first work on this pair of images, then I'm going to work on this pair of images, then I'm going to work on this pair of images, and so on, right? You kind of push your calibration forward as you go along the sequence. One part where that gets a little bit complicated is, it's certainly possible in a movie shot that I may move the camera around, then maybe the camera slows down a little bit, that speeds up again in terms of physical path. And so instead of just kind of moving along pair by pair, another thing that I could do is say, okay, I'm going to choose, some subset of these cameras. So this would be what I would call a sequential approach. What I would call a hierarchical approach is to say, okay, I'm going to choose this is my first camera, and I'm going to choose this camera over here as my second camera, and this camera over here as my third camera, right? The idea being that I try and choose these cameras to be kind of far enough apart that I can robustly estimate everything. So one issue is that when the cameras are really close together, then it's hard to distinguish the camera motion from a pure rotation, right? So basically, if the camera's not moving very much and there's only a 30th of a second between the camera frames, well then, there's not going to be that much difference between a rotation and translation of the camera versus just a pure rotation. It's hard to tell those things apart, right? So instead what I would say is, okay, I'm going to choose pairs of frames that are substantially far apart, that I would never confuse with pure rotation. I'm going to estimate their 3D positions, and then I'm going to fill in the gap between these guys with triangulation and resectioning and so on, right? So that kind of idea is probably going to be more successful than pushing it one by one, just because the ambiguities and the errors that you get when you're just pushing a camera image at a time may be, not as good as if you were to say, okay, I'm going to choose a priori the best cameras out of my whole set, and then I'm going to fill in the stuff in the middle, right? So this kind of keyframing approach is generally probably a good idea. And so, when the camera's not moving very fast, maybe you could take those keyframes to be hundreds of frames apart, right, as opposed to just taking every other, every frame, right? The other thing I'm going to mention here, only in passing, is that just in the same way that there is this fundamental matrix that relates every pair of images, there's also this concept called the trifocal tensor, which sounds fancy, but basically the trifocal tensor is something that relates triples of images. So like F, but relates triples of images. Right, this thing is a lot harder to work with, certainly on paper, because instead of having this kind of relationship between correspondences in image 1 and image 2, you've got this kind of mutual relationship between correspondences in image 1, image 2, and image 3, and that's represented by this kind of 3 by 3 by 3 matrix that's hard to visualize and hard to talk about on paper, right? But it is good for basically, so it's kind of more robust in the sense that, it ties, the triples are tied together kind of more tightly than the pairs are. And so you can kind of apply the same idea as a sequential thing, except I would use the trifocal tensor between every triple of frames, right? Again, that process mathematically is like a little bit hairy to write down and talk about for you guys, but that also is a very viable approach for these kinds of problems. And so there's a very famous paper called Threading Trifocal Tensors that talks about this. Okay, so this is the idea, and I think that at this point, so this is kind of where I'm going to stop for the day, but basically the idea is that at this point, what I have is we can assume that I have a good estimate of the camera matrices and a good estimate of these scene points, so that the error between every projection and its kind of model is low, but we have these ambiguities. Right? If I were to take all these camera matrices and multiply them by this, and all these scene points and multiply them by that, where this is some 4 by 4 non-singular matrix, my distances would be exactly the same, and I wouldn't be able to disambiguate which of these things might be correct. Okay? And so the next step is what's called Euclidean reconstruction, which basically means pushing our way up to something that we will trust as a reconstruction. And so instead of starting again to that now, I'm going to save that and talk about it starting next time. Okay, so any questions about this first phase? All right, so let me shut stuff down here.